Hello and welcome to another video. Last time around we looked into arithmetic shifts and logical shifts. Arithmetic shifts seem to work for signed numbers because they brought in ones from the left hand side into the hexadecimal numbers. Logical shifts introduced zeros from the left hand side. What we're looking up today is rotations. These are different from the logical and arithmetic shifts. These are rotations. More specifically, we're looking at rotate right. So that's the command we're working with, ROR, rotate right. Let's dig into the code step by step, one by one line at a time. I have these bunch of lines set up here. I'm going to go ahead and step through them. I've stored 13 into register R2. So that's 13 is D in hexadecimal. So you see D here. And then I'm going to rotate right the value stored in R2 by 2 bits and store the resulting number in R3. And this is the same convention that we have been using all this while. We have the destination register first, then we have the register that we want to work on, and finally the amount of rotations that we have here. So again, we want to rotate R2 by 2 bits and store the result in R3. And the direction of rotation is right? Because it's ROR, rotate right. So let's go ahead and see what do we get. So D, or 13 in decimal, or D in hexadecimal, became 4 and 3, right? So those are the most and the least significant bits. Why did D become 4 and 3? Let's have a quick look at what happened really. So we started off with this. This was our decimal. These are all the bits, all 32 bits, and we can see D13 here. 1, 2, 4. Yeah, 1, 4, and 8 are turned on. It's equivalent to 13. 1 plus 4 plus 8, and that's D. And we rotate 2 bits to the right, which means this 0 and this 1, they rotate to the right, and they become just like these numbers here in red. Okay, so they move out of the original 32 bits. 1 moved here and 0 moved here. This is equivalent to them being rotated and placed back into the hexadecimal number. So notice 1 went out first, and this 1 is now appearing right here. 0 went out next, and this 0 is now appearing at the back of this hexadecimal number. And these two numbers, these two bits, have also moved to the right by 2 bits. So effective, and these are zeros, we can't see really what's happened here, but these are all zeros that have moved to the right hand side by 2 bits, all of them. So all bits basically rotate to the right by 2 bits, and the 2 bits that we see on the far right, the least significant side, they rotate and appear back on the most significant side. So that's effectively what's happened, and the resulting number is equivalent to 3, right? So 1 and 2. So these bits have turned on. This is equivalent to 3, and when these 2 bits that moved out are rotated and placed back, this makes the equivalent number as 4, right? So 1, 2, and 4. The 4, this bit is turned on, so this is equivalent to 4 in um, decimal. Which is why we are seeing 4 and 3 in our register, destination register R3. So that's the idea of rotate right. This is what rotation on the right hand side is doing. It's taking the last 2 bits and bringing them or rotating them back into the hexadecimal number on the most significant bit size. So that's what it's doing. But this is not it, because we also want to rotate to the left hand side, but we do not have a command for that. So what do? Consider this case where we want to rotate this exact same number, D13, to the left by 12 bits, meaning these 4 bits are required to be appearing here. So, and this is a 12-bit rotation to the left, right? This is the first one. It moves 4, 8, and 12. So first bit appears here. So, and then the 3 bits follow. So all 4 bits are basically rotated to the left, and they appear here. But we do not have a means to do a rotation to the left by 12 bits. But the idea here is implementing a rotation to the left by using a rotation to the right. How do we do it? We do it like this. Rotation to the left is equivalent to a rotation to the right by a different rotation number. we use the total number of bits and we subtract the rotation that we intend to do, 12. So rotation to the left by 12 is equivalent to a rotation to the right by 20. 32 minus 12 is 20. So let's go ahead and see what do we really get by rotating our original number by 20 to the right hand side. We should expect that this gives us this result, which is effectively a rotation to the left by 12. So again, moving 13 into R8, and we have D, which is 13 into R8, and we're going to store the result in R9 this time, and we're going to rotate 20. Okay, let's see what do we get. There you go. We see D appearing right here. So it's effectively moved 12 bits to the left by using a rotate right command with 20 rotations to the right hand side. I hope this makes sense. If there are any questions, happy to discuss them in the comment section. I'll see you in the next one. Thank you.